All right, it is 2, so let's get started here. So just as a reminder of what we were talking about, we were looking at enzymes on Monday. So we looked at the different classes. We talked about induce fit, where when the substrate binds, the enzyme changes, versus lock and key, where it's already a perfect match. Talking about how enzymes can be permissive, looked at the difference, explained the differences. We were talking about cofactors, looked at some terminology like holoenzyme, which is the complete enzyme plus substrate, apoenzyme being just the enzyme without the cofactor. And then we ended here where we talked about transition state. We talked about delta G double dagger, where delta G double dagger is just the energy from the reactants to the transition state. So it's that gap here. And this gap really determines the speed of the reaction, right? The bigger this gap, or the bigger the value of delta G double dagger, the slower the reaction is. So how enzymes work is that they lower delta G double dagger. And mathematically, we can calculate the rate using this equation. The rate of our reaction equals exponential of negative delta G double dagger divided by RT. R is a gas constant, so that's a constant, multiplied by the T in Kelvin. So T in Kelvin, and that's the gas constant. And looking at this graph on the right, enzymes will never change delta G reaction. Now, delta G reaction is the energy difference between reactants and products. So an enzyme will never touch this value. The only thing an enzyme does is it changes delta G double dagger. Now, when looking at delta G reaction, if delta G is negative, that's an exothermic process, then your products are lower than your reactants. If delta G is positive, which is shown right here, so if delta G is positive, that would be endothermic. And so the energy of your products would be higher than your reactants. So we have two different situations there, exo and endothermic reactions. So we're going to continue to look at transition states here just a little bit, although I mentioned a lot of this talking about the last slide. So we talked about transition states. There's also something called an intermediate. Now, intermediates don't happen in every reaction, but they are possible. And an intermediate is being shown on this bottom left graph here. What an intermediate is, it's a stable product that's not your finished product, where you did one reaction, which is shown on the left side of that graph, and now you have created something that you can measure. It exists for a certain period of time until it goes and makes the product. So here, this is a two-step mechanism, right? Our first step is going from our reactant A and making our intermediate. That has some energy to go along with it, and it has some speed to go along with it. Then our second step is to change our intermediate into our product P. Again, that has some energy and some rate to go along with it. These two different colors are showing you different speeds of reaction. And in the blue reaction, delta G double dagger, it's higher in the first step than in the second step. So for blue, the first step is rate limiting. That is, the first step takes the longest. In the red curve, delta G double dagger is higher in the second reaction. So the second step is rate limiting for the red curve. And by rate limiting, I just mean the whole reaction is, the speed of the reaction is based on that step. The rate limiting step is always the slowest step, and that determines the overall speed of your reaction. Again, mentioning on our next plot to the right of that, catalysts. Like I said on the previous slide, all catalysts do is that they lower delta G double dagger. And the amount that they lower that by, it has a weird name. We call it delta G double dagger, because it's the change of G double dagger. So that's why it gets two deltas, because already that first hump is already called delta G double dagger. And so an enzyme's changing that value. So that's why it's delta G double dagger. Something that always confused me as a student. So in the blue curve, the first step is rate limiting. In the red curve, the second step is rate limiting. That's why I wrote them in different colors like that, because you have to look at different curves. The red curve is a different reaction than the blue curve on the left-hand side there. All right, so some math to go with this. If we want to know how much a reaction is sped up by a catalyst, this is the equation we want to use. Rate enhancement equals exponent delta G G double dagger. So how much did you lower that delta G double dagger by, divided by RT. So that is how we can tell how fast we speed up this reaction. Again, something to notice: a catalyzed reaction does not change the energy of the reactants, and it does not change the energy of the products. So delta G never changes. The only thing that changes is delta G double dagger. And remember, delta G double dagger tells us how fast a reaction goes. So by lowering that amount, that is how we speed up our reaction. So that was a lot of information. So is there any questions or clarifications about the amount of information or any of the information I just went over there? So you lower that and it goes faster, yes. Because delta G double dagger is a rate limiting step. So if you lower delta G double dagger, you speed it up. Just by going to the previous slide, right? The rate of a reaction is based on delta G double dagger. The bigger that value is, the slower it goes. So if you lower that value, the faster it goes. It's almost, the way I always think of it is running up a hill. So imagine that you're at point A and you want to go to point B. You have two paths. You have this path, or you have that path, and both of those are hills that you have to run up. Which path is faster? Obviously, green would be faster if you're running. It's the same idea with enzymes, right? If I lower this hill, I can make it across that hill faster, and I can do my reaction faster. That's what an enzyme does. It lowers the energy of the transition state. Because remember, the top of this hill is our transition state. So it's lowering the energy of the transition state. All right. So here's a little review just to make sure we're all paying attention. And I do have a poll for this. Based on what we talked about Monday and today, if you had to describe an enzyme to me, which of those 3 sentences would be the best? Just make sure we're all on the same page here. So take a minute and try to answer that. All right, so I'll end it there. So the majority of people selected B, and with some people selecting A. So the correct answer is B. What an enzyme does is that it speeds up a reaction to make it go to equilibrium faster. The reason why A isn't right is because the definition of like extremely fast, and also a catalyst or an enzyme, right, doesn't necessarily have to make the reaction go extremely fast, however you want to define that. All it has to do is make it go faster. Even if it increases it by 1%, that's still technically an enzyme or a catalyst. And remember our basic general chemistry, right? So, and we'll probably talk about this term a little bit later, but in basic general chemistry, we have this term KEQ, right? So if we have a reaction going to A to B and it's reversible, KEQ is the concentration of B divided by the concentration of A. And for every single reaction in the world, it has some value of KEQ that says at equilibrium, the ratio of B to A is this. And actually delta G, I'm getting a little bit off topic in my explanation here, but I just want to make sure I explain it fully. So delta G, we can calculate delta G based on KEQ, which also is a Gen Chem 2 term or thing that we learned there. So KEQ is the ratio of products or reactants at equilibrium. What an enzyme does is that it makes us get to KEQ faster, right? That's the best definition of an enzyme that you can give. It increases the rate at which you approach equilibrium relative to an uncatalyzed rate. So it'll make equilibrium get there faster. And I'm glad no one picked C. If a reaction is thermodynamically unfavorable, enzyme's not going to do anything to change that. So the correct answer is B. All right. So what else do you need besides amino acids sometimes for an enzyme to work? What is that term called again? And can you name all the different types of these things? Cofactors. Yeah. So remember, cofactors are your molecular teeth. Um, enzymes are just made out of protein. Sometimes you need something else for the enzyme to work. So it could be metal ions are one type of cofactor, or if they're organic, they're called coenzymes. If they are not always attached, they are a co-substrate. And if they're always attached, that's a prosthetic group. So that's a little bit of review for us, just to keep those in your mind. When we're talking about enzymes, we're talking about protein, and usually, not always, usually plus something else. That's something else called a cofactor. All right, so this one you kind of have to draw on your own. Well, first off, the first question is, what's the difference between a transition state and an intermediate? And once we have that definition, you can redraw this, or if you have the PowerPoints printed out, that's great too. Label where you're going to find a transition state and intermediate on this graph, and tell me, based on this reaction that I'm showing you, is this graph thermodynamic, or is this reaction thermodynamically favorable or not? So let's see if we can read some reaction coordinates. That's what the x-axis should say. It should say reaction coordinates. So take a minute, try to think about all those terms and see if you see if we understand them. All right, so hopefully you thought about this and attempted it. So first off, transition state in an intermediate. The best way I can, the simplest way to explain these are an intermediate is stable, transition state's unstable. What I mean by that is that a intermediate can exist on its own outside of the enzyme. It can be floating around. You can measure it. A transition state does not exist like outside the enzyme. You can never measure it because it forms and breaks so fast that the only way you know it exists is really through some clever experimentation or a lot of theory, a lot of physical pchem. So that's my simplest definitions. Intermediate is a stable compound. Transition state is not. Where can we find these? Transition state is every time you see a giant hump. An intermediate is this little valley. And the little valley is telling you this is an area of stability. Because imagine that you are a runner again and you find yourself in one of these hills. Like you could go up and get tired and come back down. You could go up this way and then come back down. And that's really the way to think about these reaction coordinates. Like you want to stay where it's flat. If you have to go up a hill, that takes work. And so you rather not do that. And is this reaction thermodynamically favorable? No. Delta G is positive because the energy from the reactants to the products is higher. So there's a big old energy gap there. So this is actually a positive delta G. This is not a thermodynamically favorable reaction. All right. Is there any questions about the terminology or anything to do with the ideas presented here or any idea we talked about so far? All right. If there's none, we can move on. And it's time to do everybody's favorite thing, math. All right. So we talked about two reactions and we haven't done anything to use those reactions. I'm going to ask you to do some calculations on test 4. So let's practice these calculations. So staphylococcal nuclease. I want you to tell me how much it reduces the free energy of its reaction. Everything you need to know about this, doing this equation, is given in the table on the bottom here. And I'll rewrite it because it might be cut off there. So for staph, non-enzymatic reaction rate is 1.7 times 10 to the minus 13th. My reaction rate here is 95. My rate enhancement is 5.6 times 10 to the 14th. So my question is, what is the decrease of delta G double dagger due to this enzyme? See if you can figure out what I'm trying to say and see if you can figure out how to do this calculation. I'll give y'all about 3 minutes to muddle through it and try to take a stab at it before I show you the way. But please do take a stab at it. That's the best way to learn, is through struggle and pain. But if you have questions while doing this, feel free to shoot me, I guess, what would it be, a private message? Or I can actually tell you the answer too if you get one. All right, so hopefully you tried it, thought about it at the very least. So what am I even asking you to calculate? I'm asking you to calculate the decrease of activation free energy, which is delta G double dagger, also known as delta delta G double dagger. Remember, that's what an enzyme does. It changes delta G double dagger, which we call delta delta G double dagger. How do I calculate that? Well, it's this equation. Rate enhancement. Well, we do have a rate enhancement for this. So rate enhancement is 5.6 times 10 to the 14th. So I get that right from the table, is equal to the exponent of delta delta G double dagger divided by RT. R and T are given. All right, a little bit of math for you. I'm trying to solve for this variable. However, I'm taking the exponent of that variable. You cannot do anything to something that you're taking the exponent of without getting rid of an exponent. So anything that is e to the power of, anything in that box, you are not allowed to touch mathematically unless you get rid of the exponent. And the way you get rid of an exponent is that you take natural log of each side. So natural log of 5.6 times 10 to the 14th equals delta delta G double dagger divided by RT. When you take the natural log of an exponent, they cancel each other out. It's almost like if you're doing 10 to the power of something and you log each side, you cancel out 10 to the power of something. So good thing to remember, natural log and exponent are kind of like opposites of each other. If you take the natural log of something that is you're taking the exponent of, they cancel each other out. All right, so R is 8.314. T is 298. So this has to be in Kelvin. You cannot use temperature in Celsius for this calculation. So a reminder, just add 273 to it to get it to Kelvin. When I do this, I should get 33, and so I'm just solving for delta delta G double dagger. So you multiply each side by RT, right? And if I did my calculations right, delta delta G double dagger equals 84135.76 joules per mole. All right. So any questions about the math there or the logic? All right, if there's none, I'm going to assume everybody has a good handle or at least was able to follow along what I did. Got one more math question for you then. Assume that you have an enzyme. And this enzyme, the way it works is that it makes a hydrogen bond. And every time you make a hydrogen bond, you lower free energy by 40 kilojoules per mole. Therefore, if you have an enzyme that forms one hydrogen bond, how much faster are you going? What is your rate enhancement if you lower this by 40 kilojoules per mole? So this one's a little more straightforward. So I'll give people, again, a couple minutes to work on this. Try and figure it out. Try to calculate rate enhancement for me, and I'll get back to you in a few minutes and show you how this has worked out. All right, so let's see if we can figure this out. So R, see it's not on here, but it was on the previous page. R equals 8.314 joules mole Kelvin. And 25C is 298 Kelvin. Okay, first thing we should do is we should convert our delta delta G. So that's what this is. That's saying I'm lowering my reaction by 40 kilojoules per mole. And R's in joules. So you can't take something that's a kilojoules and divide it by a joules. So they need to be in the same unit. So I'm going to convert kilojoules to joules. For every 1,000 joules, that's 1 kilojoule. So this is 40,000 joules per mole. Now, something else that's going to be weird, right? And I'm going to write it and then I'll explain it. The way you solve this is you do rate enhancement is equal to exponent 40,000 divided by 8.314 times 298. And you might be wondering to yourself, why is it not negative 40,000? So if we take a look at our reaction coordinates here. So let's say the black is our uncatalyzed and this brownish red is our catalyzed. So this is our reaction that's actually happening. And I lowered it by 1 hydrogen bond. So this energy gap, let's say this was like 120 kilojoules, the top of this. And so this one would be 80 kilojoules if I'm lowering it by 40. And so my change is not a negative amount when I'm looking at that. When you do delta delta G and you're lowering something, you always want to put in the positive number you lowered it by. So the change of it was a 40,000 change rather than a negative 40,000 change. A negative 40,000 change would have meant that your enzyme actually went to 160 and it would have slowed it up. So just keep in mind when doing this, for an enzyme, delta delta G will always be a positive value, even though we're talking about, lowering energy here. It's weird, I know, doesn't make sense. Just let it stew. But all you need to remember is that delta delta G should be a positive value for rate enhancement. Right, so when we solve this, our rate enhancement, if I did my calculation right, is 10,271,031. So by making that 1 hydrogen bond, we sped up our reaction by 10 million. It goes 10 million times faster by just creating that 1 hydrogen bond than it did previously without that hydrogen bond. All right, any questions about that math or that idea? All right, if not, well, looks like we do. What's the unit? Rate enhancement does not have a unit. Because delta delta G would be joules per mole. And you're dividing it by something that's joules per mole K multiplied by K. So the K's cancel out, joules per mole cancel out. And this is actually a thing in math. And anytime you see an exponent, you cannot take the exponent of something that has units. So anytime you use exponents in an equation, your answer will never have units. So exponent is always unitless. Yep, so rate enhancement is unitless as well. All right, so that ends this PowerPoint. And I will go to what we had scheduled for today. Took a little bit longer than I thought it would, but that's okay. So our first slide here is actually a little bit of a review from Monday. So I'm going to pop up a poll. Actually, I'm going to do one thing. I'm going to move this table up so you can see it. And then I'm going to shrink this down so you can see it so it's not cut off. Okay. So what I want you to do is I want to see how well you remember your organic and your general chemistry. I have 4 reactions here. I want you to tell me what type of enzyme would catalyze these reactions. So I have the poll up for you. Tell me for reaction A, B, C, and D, what type of enzyme would catalyze those reactions? Was this one of the homework questions? It very well could be. I know I originally got this from the book. I mean, chemistry is a big part of the name of this course too. So, and organic chemistry is a prereq for a reason. Well, at least we know our ligases. Okay, we'll do about 30 to 45 more seconds, and I'll put all you out of your misery and tell you the answers. I know it's been a long time. Does Biochem 2 have a lab? It does not. Nope. Which, if you're thinking about signing up for Biochem 2, I would advise you to look into it soon. It is filled up surprisingly. Just to give you an idea of the numbers, 2 years ago, we had 3 people. Last year, we have 10 people. This year, we're already up to like 22 people signed up. And I think the maximum set at 30. So just make sure if you're interested. All right. Well, this told me one thing. is that people aren't confident in their chemistry, which is okay. That's why I asked this question. So A is a isomerase. It is not a transferase because I'm not transferring a group from one place to another. All I'm doing is moving this CH3 over to the other side. I'm changing the chirality of this group. So I'm doing an isomerization reaction because I'm just isomerizing a group. To be a transferase, I would have to like bring in a new functional group and replace it with my NH3 or something like that. B, that is a gotta get my paper again. I gotta pull up the poll. Sorry, I want to see what people said for B. So B, we have oxidoreductase, and we have lyase and transferase being the answers. B is a lyase. So you are taking the group of COO and you're eliminating it, and you're forming double bonds to go with that group that was just eliminated. So you went from this down to that. So that's technically a lyase. C is in, let me see what the people said. Yeah, the majority of you got C right. That is an oxidoreductase. Yeah. So here's a good tip for biochemistry. If you ever see NADH or FAD, either one of those two molecules in a reaction, that's a redox reaction. Inside the cell, we need certain molecules to do redox reactions. And like 90+% of the time, those molecules are either NADH or FAD, I guess H2. So that's oxidoreductase. D, this is the one people got, ligase. ATP is a straight giveaway. When you see ATP and you're like making a new bond, that would be a ligase. So just a little review for the type of reactions. Make sure you just review yourself on what are the difference between these different 6 reactions. So because for this, the next couple of PowerPoint, well, this PowerPoint in specific, we are going to do mechanisms. Those of you who loved electron pushing in organic chemistry, we finally got to that section of the book. Those of you who hate electron pushing in organic chemistry, it's relatively painless in Biochem 1. Biochem 2, there's a lot of it, but Biochem 1's not too bad. So we're going to look at mechanisms now of enzymes. And we just start with a very simple class of enzymes that can do acid or base reactions. So we're looking at the reaction where you take a keto group, you make it an enol group. So it's shown here, your keto and your enol. Here's your transition state where you're half a ketol, half an enol. Normally, this reaction is super slow because you are trying to take off a hydrogen from a carbon. A hydrogen on a carbon is not acidic, so those don't want to come off. So for a ketol group to naturally go to an enol group is incredibly slow. So there's 2 different ways we can speed this up. It's through an acid catalyst or a base catalyst. And they work in slightly different ways. What an acid catalyst will do to a ketol-etol isomerization is that it will give an acidic proton to our carbonyl group here, which will help to stabilize our transition state. So if you see here, the transition states are basically the same. The only difference is that we have a catalyst that helps, stabilize the transition state. And that's what catalysts do. They stabilize transition states and make it faster, remember? So once we stabilize that transition state, the hydrogen we want to go away goes away. And now we have our enol group. And then this last part is just showing you how to remake the catalyst, because if your catalyst is destroyed, that's no good. Base catalyst, different idea. Here we have a base that's attacking this hydrogen on the carbon. But again, the transition state is being stabilized. So that's what speeds it up. And our last step here is that we are just needing to remake the enzyme. So in general, an acid catalyzed reaction is you give a proton away. A base catalyzed reaction is that you take a proton. So acid you're giving, base you're taking. You can have reactions that use both acid and base catalyzed reactions. And the amino acids that are used in this should be no surprise if you remember your amino acids. Asp, glu, his, cis. Cis should be a little bit of a surprise, but it has that SH there. Tyrosine and lysine. Tyrosine has the OH on top. Cis has the SH. So they can do acid and base chemistry a little bit. The last thing we're going to look on is the mechanism of one enzyme, RNase A. What RNase A does is that it breaks up RNA for digestion purposes. So when you eat something, that something probably has RNA in it, because like everything alive more or less has RNA. And so we need to digest that RNA to turn it into energy. So RNase A is secreted by the pancreas, and it is acid-base catalyst. It does both. So here, the important amino acids are histidine, and hopefully you remember the pK of histidine. Who can tell us what the pK of histidine was again? What's that number that I had you memorize? Yes, it's 6. pK of histidine is 6. What is the pH inside of a cell again? Anyone? The inside of your cell is it 2? Is it 9? 26? 15? 4? 7? 7? 7? The pH inside of your cell is 7, which means histidine is both an acid and a base. So histidine is the perfect amino acid for acid-base chemistry because it's fine being protonated or unprotonated. Remember when pH equals pKa, you're half protonated and half unprotonated. So histidine's fine being in either case. So that's why in a lot of acid-base mechanisms, you'll see histidine. So let's take a look at this mechanism. Step 1, we have one histidine attack the 2' hydroxyl of RNA. So 2' hydroxyl gets attacked, and we're taking that hydrogen away. So we're doing base catalysis up here. While down here, we're doing acid catalysis, right? So we're giving a hydrogen to an oxygen. What happens, and I'll erase this so you can see, what happens when we do both acid and base catalysis at the same time is we're breaking a bond. We're breaking the bond between this phosphate and this other base. And that's what's being shown here. We have this base leaving. This base was that base right there, or that nucleotide rather. And we have an intermediate. Here's our intermediate, where we have our phosphate bound to itself. The phosphate of the base is bound to itself, or of the nucleotide rather. And so we can't let our nucleotide go quite yet. One, because we need to restore our histidines back, and one, we need to break this RNA, this cyclic RNA. So we have the opposite reaction happen. The histidine H12 now acts like an acid. Histidine 119 acts like a base. So they switch roles, right? The histidine at top is now donating a hydrogen. The histidine on the bottom is now accepting a hydrogen. And that RNA is now free to leave. Your histidines are back ready to go, where the top can now act like a base, and the bottom can now behave like an acid. So that is a concerted acid and base reaction. And that is how the mechanism of RNA ACE works. Rather simple, again, two histidines acting like an acid and a base. But yeah, that's our first mechanism we're going to look at. So I'm gonna, on Friday, what I will do is I will ask you a question about this mechanism just to refresh yourself. So make sure you digest this a little bit. Just think about it for a couple minutes today. Otherwise, we'll end it here. I'll put up a homework in a little bit here. If you have any questions about anything, as always, please do let me know. Otherwise, hope you have a lovely rest of your Wednesday. And I will see all you soon, I hope. Take care, everybody.